So thank you, Valentin. Thank you very much for the organization of this workshop. And thank you very much as well for your kind invitation. So I will speak on stochastic particle systems with singular interactions. So I will start smoothly with systems with smooth interactions, and then I will explain what happens when singular interactions occur, and I will examine especially new type of singular interactions which arise in models in neurosciences. So, three main parts in the talk. First of all, I will introduce the so-called McKean-Vlasov stochastic differential equations. And, sorry. That's okay. So I will start with the standard interaction kernels. So that's a standard theory, let's say, and then I will switch to examples of new models where singular interactions are absolutely necessary. They come from physics, and I will tell you parts of the difficulties which arise due to the singularities. And then I will focus on singular interactions coming from models of membrane potentials in neuroscience. Okay, so first part, McKean-Vlasov stochastic differential equations with standard interaction kernels. So to start with, I get rid of interactions, and I just summarize a bit of well-known results on stochastic differential equations without interactions. So given a Brownian motion W, capital X will denote the solution of this equation. Here, the integral of sigma of xs with respect to dw is an Ito integral. And I recall the well-known fact that this stochastic differential equations provides a way to construct probabilistic interpretations of linear parabolic partial differential equations. So if A denotes the matrix sigma, sigma star, if capital L denotes this differential operator, so the gradient of B scalar gradient, plus 1/2 the sum over gk of A gk times the second derivative with respect to the direction g and k. So look at this parabolic problem. So f is a test function, that's the initial condition of the PDE. And look at du over dt equal to L of u. So if all the coefficients are smooth enough or satisfy other ad hoc conditions, we are able to prove that this PDE has a unique solution, which may be either a smooth solution, classical solution, or a weak solution in the viscosity solution sense. And this unique solution is in fact given by this formula, the expectation of the test function f applied to the process capital X, this guy. Okay? So ut of x, the solution of this PDE, is equal to the expectation of f of xt starting from x at time 0. Okay, and now if you look at this representation, just by duality argument, you deduce that the probability distribution of xt, call it mu t, this mu t is a measure, it's a probability measure, which solves this linear PDE, d mu dt, d mu t over dt is equal to L star mu t, where L star is the formal adjoint of capital L, obtained by integration by parts techniques. So that's this operator. Okay, so that's the main object to understand the next slides. We have a way to represent the solution of this PDE, the Fokker-Planck equation. It's to solve the stochastic differential equation, and the probability distribution of the stochastic differential equation is the solution, the weak solution of this equation. Okay? Well, so let's go on. I will speak just a little bit about numerical issues. One of the main consequences of the preceding slide is that it allows one to develop stochastic numerical methods to solve the deterministic PDE, either that one or that one. So look at this, for example. If you have independent samples of capital X, the solution of the stochastic differential equations, then you can use a Monte Carlo method to approximate ut of x. And it appears to be extremely useful, for example, when the dimension of the PDE is very large. So then the stochastic methods may compete and even are much more efficient, maybe much more efficient than deterministic numerical methods. Or if you look at this equation, and that's the main thing to remember for the next slides, the empirical measure of your samples of capital X will be an approximation of the measure mu, solution to the Fokker-Planck equation. Okay? The point is that you can't solve exactly the stochastic differential equation, of course. So one way to solve it numerically is simply to run this Euler discretization. So here you discretize in time the Lebesgue integral or the Riemann integral in the stochastic differential equation. And this is an Euler discretization, very naive but very efficient, of the stochastic differential, the stochastic integral. And the point is that the simulation of that scheme uses only the simulation of Gaussian, independent Gaussian random variables, because the Brownian motion has independent Gaussian increments. So again, here is the formula, the numerical formula you run on your computer in order to approximate the expectation of f of x bar t, which should be close to expectation of f of capital X t when the discretization step goes to 0. And again, this quantity, expectation of f of capital X at time t, is an approximation of the solution of the PDE du over dt equal to Lu. Okay? What about the statistical error, which means the error due to the fact that you approximate the distribution of x bar by the empirical measure of your simulations of the Euler scheme? So, of course, you have in your hands either the central limit theorem or much more precise estimates such as Berry-Essen inequalities and so forth. So basically, these non-asymptotic estimates tell you that for every capital N, the error is of order 1 over square root of capital N. And there is a recent new result due to Lemaire and Stéphane Menozzi, very interesting, which tells you that you can you also control the probability that your error may take catastrophic large values. So it's a concentration type inequality, which tells you that the probability that the statistical error corresponding to capital N samples of the Euler scheme, the probability that this error takes, in absolute value, takes a value larger than script or, let's say, is controlled this way. So it goes exponentially fast to 0 in terms of the number of simulations. And it has a Gaussian decay in terms of script R. And the constant here are uniform with respect to the discretization step of the Euler scheme.
May I add something? Actually, you can remove the bias. The identity holds. Okay. We've seen that recently. It's just a comment.
Okay. So here, hypothesis, B is bounded. It's not so important for us in the story. I will tell you later on. But here, as of, for some other chapters of this analysis of numerical errors, A of x is supposed strongly elliptic. Okay, but in fact the strong ellipticity is not essential at all to control the discretization error. Actually, all papers I committed with Luciano Tubarro or Vlad Bali, and then the story was continued by many authors, including Koatsuiga, Gobet, Menozzi, Milstein, Tretyakov, and so forth. So in extremely various situations, the discretization error, that means the part of the error which tells you how you approximate the exact distribution of capital X by the approximate distribution, by the distribution of the Euler scheme, this discretization error can be expanded with respect to script n. So it's not a bound for the error, it's an exact formula. So there is no, typically there is no ellipticity condition at all. Either the coefficients are smooth, or the coefficients and f is smooth, or if f is only measurable, for example, you need to suppose that capital X is hypoelliptic, and which allows you to develop Maliavin calculus techniques. And the interest of this expansion is that then you can develop numerical Romberg-Richardson extrapolation procedures to increase the accuracy of the Euler scheme simply by running the scheme with two different step sizes and combining by a linear combination of the results. You get, instead of getting 1 over n, an accuracy of 1 over n, say, then you can get 1 over n squared, etc. Okay.
I wonder whether the problem is still open for linear drift or something. You can say, if drift is linear.
Oh yes, in fact, this result is, has been proved in very, very general context. So the drift may be, it can't be measurable, but it can be, even in some polynomial cases and so forth, you have this kind of estimates. I mean, each time you have a solution capital X which has moments of, let's say, 4 or 6 order, then you get to this kind of formula. And it's also true. It's also true for reflected diffusions and so forth. So stop diffusions, and so it's a very generic property of discretization of SDEs. So typically, when the coefficients are smooth and f is smooth, for example, to simplify, then the order is 1 over n, plus 1 over n squared, and so, etc. So keep in mind, the statistical error is 1 over root capital N, and the discretization error, if everything is smooth, is of order 1 over n, script A. Okay, now I switch to a more complex structure of dynamics, which is extremely important and interesting to represent a wide family of physical PDEs, nonlinear PDEs coming from physics. So what's the structure? So if we forget this part, and this part, then we recover exactly the same structure as before. The coefficients depend only on the solution we are looking for. Okay? But now, in the story, so I have a set of particles. I goes from 1 to capital N, so I have a set of n particles, and the motion of each particle is governed not only by its own dynamics, but also by the empirical distributions of the particles. Okay? So mu bar n is the empirical measure of the particles. So because of that, because of the fact that the coefficients depend on this empirical measure, all the particles interact. Okay? The particle x1, let's say, depends, the dynamics of x1, the coefficients of the dynamics depend on x1, and also on the sum of 1 over capital N b of xg for g going from 1 to capital N. So all the particles interact. Okay, so two main issues now. What does it happen when capital N goes to infinity? And second, why this dynamics is related to nonlinear PDEs coming from physics? And the last part of the talk, why is it related to biological phenomena and PDEs arising in neurosciences? Well, so to understand the story, for those of you who don't know so much about it, imagine that all the particles are independent. Of course, it's not true. I've just explained that it's not true at all. But suppose that they are independent. Here. Okay, so if they were independent, because of the strong law of large numbers, this quantity should be an expectation with respect to the common law of the particles. So this should be the expectation of B of thank you. This should be the expectation of B of script X XS. So that would be the law of the process, the limit process, and evaluated at script X equal to XSI. Okay, so I repeat. Imagine here there is script X. So that's the integration of a deterministic function with respect to a measure which is very close to the exact distribution of some random variable. Because I suppose that all these guys are independent samples of the same random variable. So let's call it XS, this random variable. So from the strong law of large numbers, this should be the expectation of B of script X, XS. Okay. And now I substitute the value capital XSI to script X. Okay? So that should be the natural candidate to identify the possible limit to this particle system. And actually, the theory initiated by McKean in the 70s and then continued and extended in various directions by Slittman in the 80s tells you that if the coefficients, all the coefficients, capital B, capital S, B, and sigma, are smooth enough, Lipschitz says, then the particle system propagates chaos in the sense that the empirical distribution of the particles converges weakly to a probability measure on the space of trajectories. And this probability measure is the probability distribution of the solution to this new stochastic differential equation. So this is a stochastic differential equation of a totally new type. Why? Because the coefficients of the dynamics depend on the probability distribution of the solution you are looking for. So the story is fully nonlinear, obviously. You are looking for the solution of an equation whose coefficients depend on the probability distribution of the solution. That explains you why, at least intuitively, why this structure will allow us to interpret nonlinear PDEs. And of course, so now let's come again to this formula. You can see that because U bar n converges weakly to the probability distribution of capital X, then this approximation now makes sense. And in addition, the probability distribution of X, capital X at time t, that I denote by nu t, is a solution of a new Fokker-Planck equation. So d nu t over dt is equal to L star nu t as before, except that L star now depends also on nu t, because the coefficients, so L star is a formal adjoint, as before, of the generator of this process, and the generator of this process has coefficients which depend on the distribution of the process. So, when everything was linear in the problem, in the sense that the coefficients do not depend on the distribution of the solution, the distribution of the process solves a linear Fokker-Planck equation, d mu t over dt is equal to L star mu t, where L star has coefficients which do not depend on the distribution I'm looking for. But now, in our context, we have this equation where the operator itself depends on the solution. Well, so a couple of words on both on numerical issues and on the way we play with the preceding slide in order to represent solutions to nonlinear PDEs. So how to solve the nonlinear PDE here by numerical methods? The strategy is clear. So this object cannot be solved exactly, obviously. In particular, because to discretize this equation, you first would need to know the solution to this PDE, but it's exactly what you are looking for, the solution to the PDE. So that makes no sense to simply run a Euler scheme to that dynamics. So what the solution? The solution consists in coming back to this particle system. We know, because of the propagation of chaos property, that if capital N is large enough, this should be close to the solution I'm looking for. And to discretize these dynamics, now I can run the classical Euler scheme I presented a few slides ago, because here everything depends only on the empirical distribution of the particles I'm simulating. So this system is linear in the preceding sense. And simulating this linear structure in the McKean sense, I should be able to approximate the solution to this nonlinear problem.
So you observe this xg and you count this empirical measure and then you apply Euler scheme.
Yes. Exactly. In fact, I apply Euler scheme to that dynamics.
But why does the empirical measure, it does not depend on S, on the time? Empirical measure.
Here?
No, but here, below.
Oh, I mean, this is an empirical measure on the set of trajectories. When I don't write the script, that means that I think of the object as a numerical measure on the set of trajectories. So, of course, in particular, for each S, nu bar n S is defined as the marginal at time S of this empirical measure. So 1 over n, sum over G of delta at point x, G, script S.
You transmit measure with the usual way on the set of trajectories.
Yes. Yes, and it's exactly what I understood here when I said that nu bar n converges weakly to the probability law of the solution. I mean, it's a convergence on this empirical measure on the space of trajectories converges weakly to the probability distribution of the process on the space of trajectories of the process. So it's not only a convergence at each time t, it's a convergence of the process.
It's a kind of strong convergence. Kind of
weak convergence, but in metric space.
It's a weak convergence on the Wiener space.
On the path space.
On the path space. Which is actually the due to Sneedman, this observation that we have this very strong convergence. Okay, so now it's clear we discretize the particle systems, and the empirical measure of the particles should approximate any marginals, at time marginals, of the exact solution of the nonlinear Fokker-Planck equation. I will discuss this formula on the next slide. Just one thing I would like to emphasize before going on is that in that story, and so it will be, the situation will be quite different in a few minutes when I will start to examine singular interactions. In that story, the interaction between the particles are due to kernels. Okay, I integrate the empirical measure against kernels. And for the story a part at least of the literature to be applied, I need that these kernels are smooth enough, at least Lipschitz. Okay, so just an example where we start to see some, at least not singularity, but discontinuity in the story. So if everything is smooth, let's say Lipschitz, the inequality I will show you on the next slide is well known, and the propagation of chaos is well known as well. Now let's look at an example where the situation is much less classical. Look at this scalar conservation law. dv over dt equal to 1/2 the second derivative in space of capital V minus derivative in space of pi of capital V, where pi is, let's say, C1 function. So, for example, this equation, this formula, includes the Burger's equation, but many other conservation laws in dimension 1, at least. So there are two ways of playing with this equation. Either you interpret it as the Fokker-Planck equation itself. You may do it. I'll let you the exercise to try to identify what should be the kernel script B, the function capital B, and here sigma is necessarily, capital A is necessarily equal to 1 because the diffusion coefficient is 1. So this part plays no role in the story. And here, but if you try to interpret this dynamics as a nonlinear Fokker-Planck equation, just by identifying the coefficients, then there is a major difficulty is that the kernel should be a Dirac measure. So very singular.
It is not clear whether you are talking heuristic or propagation house can be rigorously justified in such a single case. It's not clear at all. Under which condition you can justify propagation house argument on your system, on the coefficient?
Which one? The preceding one?
Yeah, okay.
As I told you, in general, as I told you, if everything is Lipschitz, then it is a very classical strategy to there does exist a very classical strategy to get the propagation of chaos. In some other circumstances, then you need to identify the discontinuity or the singularity, and then to develop ad hoc strategies. So to answer to your question more precisely, here is an example where the coefficients are not Lipschitz. So if you identify the coefficients of the nonlinear equation with this nonlinear PDE, then again you're led to a kernel which is a Dirac measure. which is very singular. But you can smoothen a bit the problem by considering that capital V should not be a measure, but you can interpret it as the distribution function. Let's say if V naught at time 0 is a function, not a measure. So if you're given a function, then think of that as the dynamics of the probability distribution of an object which should be, which should be the solution of this kind of PD. So it's really an exercise. You identify, you write, starting from that, you write what should be the dynamics of the distribution function. You integrate with respect to the kernel h x minus y, the measure nu t dy, where capital H is a V-side function. Okay? And you integrate by parts, blah, blah, blah. And then you're led to that dynamics is really an exercise. So the particle systems now read that way. So you can see it's really of that type. So capital B is, let's say, pi prime. Pi is this function. And the kernel script B, with respect to which you integrate the empirical measure, is the Heaviside function, which is not Lipschitz, of course, because it's discontinuous. So you have an example where the data of the problem are not smooth. At least they are discontinuous. Anyway, in a first paper by Mireille Bossy and myself, and then Mireille, and also in another direction, Mireille Bossy and Benjamin Jorda, all these papers could prove that, first of all, the preceding particle system propagates chaos, in spite of the fact of the coefficients are not Lipschitz at all. And in addition, what Mireille proved is the following optimal convergence rate. You take the exact solution, capital V, minus the distribution function of the empirical distribution. You take the absolute value, you take the expectation, and you take either the supremum with respect to script x, or you take the L1 norm with respect to script x. In both cases, what you get is an estimate of that type, constant over script n, 1 over n is a discretization step, plus constant over square root of capital N. That is exactly the same accuracy as in the linear cases with the smooth coefficients. Okay. Well, so the only difference is that, at least so far, the error is not expanded with respect to script n.
It was made for this example.
Excuse me?
For this example?
Yeah.
This result.
Yes, and also, of course, if all the data of the particle systems are smooth, let's say Lipschitz, then of course this estimates holds true in force.
You use H capital in the definition of V bar. What is it? It's not a Heaviside because you use Heaviside.
Excuse me.
H capital, what does it mean?
It's a Heaviside function.
That is, this result is for the example, no?
Yeah, either. So, in the example, the Heaviside function appears twice for different reasons. So here, whatever is the interaction kernel, if you want to approximate the distribution function of the empirical measure, or the distribution, that means, excuse me, if you want to compute the distribution function of the empirical measure. So that you use a Heaviside function just by definition. And then this should approximate the distribution function of nu t, the solution of a nonlinear Fokker-Planck equation, which again can be defined as the integration of capital H x minus y with respect to nu t dy. Okay, but so that explains that if you each time you want to approximate the distribution function of the solution of your nonlinear PD, then you use the Heaviside function just to define the distribution function. But here in this particular story, the Heaviside function appears a second time just because of the particular structure of the PD. And we'll see.
P in their theorem is the same P as in this equation. Right? P is of class C3.
P? Yes.
Pi.
But how does the algorithm look like? What is your algorithm? How do you approximate? I mean, it's a Euler scheme or what kind of scheme?
Here, yes, it's an Euler scheme applied to the particle system.
But Euler scheme, in each step of Euler scheme, you need to approximate again you measure, yes? Or
No.
no?
I mean, I don't need to approximate the measure. I use only the empirical measure.
Yes, but I mean, you have to construct this empirical measure at each time step. Yes?
Yes, sure.
From the previous observation. Yes?
No. At each time step, so forget the interaction kernel for a while. At each time step, I simulate independent copies, independent samples of this discrete time process. And then the empirical measure is simply 1 over n, the sum of delta of x bar at time pt over n. So that's exactly the same story here. At each pt over n, I integrate the kernels B and sigma with respect to the empirical measure at pt over n. I simulate an Brownian increments, and that leads me to the value of the positions of the particle at time p plus 1 t over n. Okay. So now, what about other PDEs, nonlinear PDEs coming from physics? In fact, all the interesting nonlinear PDEs coming from physics lead you instantaneously to singular interaction kernels, singular data. So burgers, or as I explained to you a few minutes ago, the Navier-Stokes equation in dimension 2, then the kernel is a Biot and Savart kernel, which explodes at the origin. So the propagation of chaos was proved by Ozada years ago, at least when the viscosity coefficient is large enough. And Jourdain-Méléard looked at 2D Navier-Stokes equation in bounded domains, but it's not exactly the 2D Navier-Stokes equation with boundary condition. They have to smoothen a bit the equation in order to provide the probabilistic interpretation. So there are a lot of work to remain to be done for 2D Navier-Stokes equation. For 3D Navier-Stokes equation, almost nothing has been done. And for Boltzmann equation, a lot of work has been done, but basically by smoothing the kernels. For McKean-Vlasov PDEs for corresponding to particles with electrostatic repulsion, which look like the Biot and Savart singular kernel of the 2D Navier-Stokes equation, a paper by Sepa and L'Épingle started the story. As well, I mean, in the sense that they proved that the particle system was well defined, and the limit system also. But now I will speak about a new type of structure. So it's a first example where the particles interact not by means of kernels, by much more singular means. So the story started by the reading by Mireille Bossy, Jean-François Jabir, and myself of papers by Pope. Pope is a very well-known physicist, a specialist of combustion and fluid dynamics. And he developed an approach which is a statistical approach for the turbulent flows or complex flows. So it's a way to compute the so-called Reynolds average Navier-Stokes equation solutions. So he proposed a model of interactions between particles and the complex motion of fluids. So instead of writing the macro equation, the Navier-Stokes macro equations for the fluid, propose a stochastic approach based on the motion of particles which interact with the fluid. Well, so it was not so easy to understand, to reformulate the ideas developed by Pope in mathematical terms. I mean, in the framework of our mathematical tools, I should say. But if we rewrite his algorithm, his model, what we get is this dynamics. So there are plenty of difficulties here. No, almost nothing is smooth in the story. Here you have, so I mean these functions are not smooth at all. Even you have a square root, for example, here. Here you have a very singular object in terms of McKean-Vlasov dynamics. It's not the probability distribution of USXS, which you had before to handle, but the conditional expectation of some coordinates, the velocity coordinates, with respect to the position. So that's much more difficult than the distribution of the pair U and X. In particular, it's not at all, it can be written as this object cannot be written as the integration of a kernel with respect to the distribution of the pair UX. Okay, so another difficulty is that here you have the solution to the Poisson equation, whose source term, again, is a conditional expectation. Another difficulty is that this system is hypoelliptic. It's not at all elliptic, strongly elliptic. Last difficulty, the problem is naturally posed in let's say, half spaces or in domains. So you have to add boundary conditions. And for example, in half spaces, what happens to the particles when they hit the boundary? they are not reflected as in the classical score the problems for diffusion processes. They need to satisfy a specular boundary condition. That means that when the particle hits the boundary, the velocity changes in direction instantaneously.
Summation is all jumps, or could you explain what is summation?
So that means that as the velocity changes its sign instantaneously each time the particle hits the boundary, you can represent that as a jump between v and minus, between u and minus u.
Gamma is number.
Here I don't specify.
Okay, but triangle like this and like this, it's the same. You're right, where, del, nabla. Because in an equation you have triangle in another way.
I have what?
Triangle. No, I mean this operator. Nabla.
Nabla.
In the equation,
Where is
and
nabla?
after the word where, nablas are different.
Yes, this is a Poisson equation, I just told you.
But you write where.
Yeah.
But this is different. Something. Nabla in a different.
Yes, so, I mean, what I mean here, that calligraphic P is a solution to this Poisson equation. And once you have solved your Poisson equation, you compute the gradient of this solution, and you put it into the equation. So solving this Poisson equation with this kind of source term given by conditional expectation is an issue, real issue for PDE analysis. And then what's the regularity of the gradient of the solution? That's another part of the story. So when I tell you that the analysis of these dynamics is very, very big analysis and PDE analysis and stochastic analysis problem, I mean, it's not, I don't lie. It's really a big challenge to check that this dynamics is well posed. And another issue is that you need to prove that finally, if this equation is well posed, then actually it will provide you satisfying statistical properties for the flow. And in particular, it should allow you to compute, for example, what the specialists in the field call the Reynolds stress tensor of the fluid. Okay, so I have no time to develop all the aspects of the story, very complex story. Just to tell you, to give you an idea of the difficulties, let's simplify a lot the preceding dynamics. Look at this very simple, not very simple, this simplified dynamics. So I get rid of the Poisson equation. I get rid of the singular or discontinuous function epsilon k. I get rid of the specular boundary condition. I only keep the hypoelliptic structure and the fact that the dynamics is governed by a conditional expectation of velocities given positions. Even in that case, it's not obvious at all to prove that the process XU is well defined and the corresponding particle system propagates chaos. So we could do it with Mireille and Jean-François. And then, so a part of the story depends on nice results by Francesco and Pascuzzi, Italian specialists of hyper parabolic PDEs. And Stefan also worked on that kind of PDEs. So it's an estimate, a crucial estimate on transition densities of the preceding of the preceding process, or in terms of PDE, on the fundamental solution of hyperparabolic PDEs. Well, and afterwards, Mireille and Jean-François continued to work on Pop's model, and year after year, they add either the boundary condition or singularities in the dynamics, and hopefully in a few years they will be able to solve the complete story. And recently they could prove that the pair XU is well defined even if you add in the story the specular boundary condition, even when gamma is not only the boundary of an hyperplane, hyperdomain, excuse me, hyperspace, but it could be other boundaries. So that answers to your question. And in addition, they can prove that this is a very important property which expresses the fact that typically the particles cannot exit from the domain. At least in the tangential direction. The numerical analysis is in progress. In fact, very.
Equation for x is this theorem. How dynamic for x?
X is defined as the integration of the velocity as before. Yeah. Yes, we keep that the derivative of the position is equal to the velocity. So I just focus on the dynamics of the velocity.
Is it a scalar product?
Yes, the velocity scalar, the normal at the boundary, at point where it hit by the particle at time t. So this scalar product is equal to 0. Okay, but so they are right now. They are working a lot, and they partially solved the problem to include this additional term in the dynamics, which is a very, very big challenge. But they succeeded to get very nice results. Okay, and very soon probably Mireille and Laurent Violot will publish a paper on the accuracy of the particle systems, at least in some simplified version of these dynamics. Because, in fact, of course, the model developed by Pop was a computational model. I mean, if you look at Pop's papers, the dynamics is not written like that. It's not a mean field dynamics. It's written as particle systems, exactly as in my preceding slides. So it's very important to get estimates on the accuracy we can expect on, for example, the Reynolds stress tensor approximated by means of the empirical distributions of the particles. Okay? Okay, so in my title, I wrote neuroscience. So now I switch to populations of neurons and models for membrane potentials along neurons. So I look at populations of neurons, and if I were interested in let's say, the brain of a soccer player or football player, probably I would not deal with large size population. Capital N equal to 10 would be enough, probably. But I'm interested in brain of ordinary people or intelligent people, so capital N needs to be large. So I'm interested in large populations of neurons. Okay? So that I can expect, if ever there are some interactions between the neurons, I can expect that the mean field limit I presented for the preceding particle systems play a role in the story. And my personal interpretation is that if it's true, that means that God, instead of implementing the nonlinear PDEs in our brains, found it extremely useful to create brains with finite but large number of neurons in order to compute mean field limits, to approximate mean field limits. But the main part of the information computed by the brain could be represented by the midfield limits, McKean-Vlasov dynamics I discussed in the preceding slides. Okay? The point is that, as we will see in a few minutes, if we are interested in modeling the way neurons interact, there is no interaction kernel. Maybe in a we could include later on interaction kernels, but probably the main part of the interactions are not governed by kernels, as we will see. So, a neuron works as a membrane, and along the membrane, the electric potential varies. And biologists used to think that the brain codes information, at least partially and sometimes mainly, not by the values of the electric potentials, but much more by the times, the sequence of times at which the membrane potentials reaches a given threshold. So typically what happens is that you have along the membrane potential, you have ionic channels which are open and closed. When they are open and closed, when you open or close these ion channels, then you make vary the electric potential along the membrane. Okay, and each time the electric potential at some point reaches a given threshold, that more or less instantaneously the electric potential is reset to 0. Okay, so that's the way the neurons work. And again, the heating times of the given threshold is much used by the neuron system in order to code information. So it's exactly what is written here. And at each time the electric potential reaches the threshold, let's say 1 to simplify the notation, then people say that the neuron is spiking. And when the system spikes, it means when any of the potentials UI of neuron system reaches the threshold, then that's the number of times the neuron number I reaches spikes, and then what happens is that not only the potential I is reset to 0, but also it affects the value of all the other potentials. So all the other potentials are increased by the value 1 over capital N. So the potential I goes from 1 to 0, and all the other ones increase by 1 over capital N, just to respect the conservation Ohm law. Okay? So let's try to write a dynamics for the membrane potential. So suppose that you have, let's say, deterministic coefficient B, which would describe the dynamics of the potential if there were no chemical reactions and no interaction with the other neurons. The Brownian motion here, just modeled by the Brownian motion here to simplify, the fact that we have chemical reactions with the medium. And here is the fact that at each spike we are reset to 0. And when the other neuron spike, then we are increased by a factor alpha over n. So it's not exactly 1 over n, as I just told you. Here it's alpha over n, and alpha, let's say, the strength of synaptic connection. So you can see that, again, the particles interact. Each time one particle spikes, then all the others are affected. But there is no interaction kernel in this story. The interactions come from the heating times of the particle systems. Okay. So, questions. Does this particle system propagate chaos? And what's the mean field limits of the particle systems? Okay, so people from PDE analysis studied this problem by PDE analysis techniques. So in particular, Carrillo, Pertam, and their co-authors. So if you look at the probability distribution of xt, so I suppose here for a while that this particle system propagates chaos. Xt would be the mean field limit, as before. So suppose there is a mean field limit. Let's mu t is probability distribution as before, but suppose you can prove that the mean field limit has density for all t. So nu t has density for all nu t, and let's call it pty. So it's not a zero assumption. I mean, in the next slide we will prove it. Okay. So the density of the mean field limit of the particle system capital X. So just maybe to help you to follow, if ever you're lost. When there were interaction kernels, this was the mean field limit of the particle system. Okay. And now, so I suppose there is such a process here, and Pt is the density of X at time t. Then for some reasons I don't explain, but PT should solve this nonlinear Fokker-Planck equation, where again there is no interaction kernel in the story, but there is a nonlinearities. The nonlinearity is due to the fact that here we have E prime t, which is the derivative with respect to the space variable of p t at point 1. 1 is a threshold. So this expresses first that the nonlinear part of the story, the fact that the particles interact, and also the very non-classical boundary condition at point 1. And there is a source term which also is related to the fact that the nonlinear process should spike at point 1. Okay, so this is a non-smooth and nonlinear equation. And what's the analytical results? What are the analytical results? For example, one of the results tells you that for any alpha, alpha is the strength of the interaction when one of the particles spikes. For any alpha, there is an initial density, P naught, such that blow-up occurs. What does that mean, blow-up, in terms of, so for the PDE analysis, that's clear, the solution blows up. And from a stochastic point of view, I just tell you, when one particle spikes, all the other ones, the membrane potentials, all the other membrane potentials increase with the value 1 alpha over n. If ever all the particles are very close to 1, what does it happen? Let's say the particle number 1 hits the boundary. It's reset to 0. But instantaneously, the second one hits the boundary. It's reset to 0, but instantaneously, the first one is increased by 1 over n, alpha over n, and the last but two other ones increase of 1 over n as well. So it could be a cascade of spikes, instantaneous spikes. All the particles spike at the same time. So the stochastic system cannot be defined. Means okay, and it could be such a phenomenon could be interesting to model, for example, epilepsy. But if you're not interested, if you're interested in, let's say, a smooth behavior of the brain, so not epilepsy, not diseases of that type, then the system should not blow up.
You said this about coefficients. Suppose B has negative drift, strong negative drift.
Doesn't play any role in the story. It's not. It doesn't play any role in the story because here I suppose that the diffusion part is equal to 1. And if there is a sigma which is strongly elliptic, it doesn't play any role as well. I mean, the probability that your particle hits the boundary in finite time is equal to 1. So we on dimension 1, the process is recurrent, so there is no problem at that time. Okay, so now, recently with James Inglis, so, excuse me, before. So recently, François Delarue, James Inglis, Sylvain Rubenthaler, and Étienne Torré looked at the preceding system, so that exactly the nonlinear process, the mean field limit I just presented in the preceding slide, it's rewritten here. So they could prove that for any epsilon. There exists an alpha 0 positive, such that if at time 0 all the particles have an initial distribution with this Dirac measure, not a density, which explains the difference with the Carrillo and Pertam analysis. Carrillo and Pertam claim for every alpha there is an initial density. Here the claim is I can choose a very large set of values of alpha such that if the initial condition is a Dirac measure, then there is a unique solution which doesn't blow up to the mean field limit. And the particle system propagates chaos.
The boundary equals 1?
Yes. Because of that. Because of minus t. So the limit system spikes. The particle system propagates chaos. The mean field limit is well defined. And there is, for all t, there is no blow up. And there is the PD explanation. I mean, the PD counterpart is that actually what I denote E prime of t in the preceding slide, that is d over dt, the expectation of mt. So this is the expectation of mt is actually this guy.
You compensate with the number of particles jumping out of the boundary, something like this.
No.
Because xt is moral equals than 1. Tau k is defined with xt minus moral equals than 1, but 1 is the boundary.
Yes, but that means, I mean, I could have written equal 1. It doesn't change anything. The process is continuous. The process is continuous, except at times tau where it hits 1. Then it resets to 0. And between tau k and the next tau k plus 1, the path are continuous.
So you can write equality. You can write equality.
Yes, I could have written equality. Doesn't change. Okay, so that's a model for which, if the initial distributions are Dirac measures, or maybe other distributions, not all because of Carrillo and Pertam result, but at least certain family of initial distributions, the system doesn't blow up, but following in view of Pertam and Carrillo results, the system may blow up if you are unlucky with your initial condition. So with
Actually, is it important that you have one point, or it could be some of diagnoses?
Some of
diagnoses?
What do you mean?
Probability distribution of the diagnoses, for instance.
At time 0? You mean a discrete measure?
Yes.
Yes, I think it doesn't change anything the same. So with James Inglis, I just finished a paper. Well, we were interested in a model, so we examined the following version of the preceding model. And for this model, there is no blow-up, never. Whatever is the initial distribution. And so what we did is that, in fact, we smoothened the spiking effect of the other neurons by means of a kernel G acting on the empirical distribution of the heating times. And actually, this model is not due to our imagination. It appears in papers in neuroscience literature. And compared to the other model, we added the fact that the dynamics of the membrane potentials may diffuse. So we have diffusion coefficient sigma. which is no more equal to 1. And also we introduce non-symmetric interactions between the neurons. And again, it's a biological fact. So, as before, the question is, does the system propagate chaos? What's the midfield limit of this system? And is there any blow-up in the story? So why is it reasonable to take into account this smoothing effect? Is that, in fact, in the preceding model, excuse me, that one, there is no space effect in the story. I mean, a membrane has a length. And all the neurons are connected. I mean, all the neurons of certain families. There are plenty of families of neurons. And each family, in each neuron, each family, connect to a soma. So the structure of the brain, the geometrical structure of the brain, something like that, at least simplified. So you have a soma, a family of neurons which interact and are connected with a soma, another soma which is connected with the first one, a family of neurons all connected to the second soma, etc. But it's very complex between this neuron here can interact also with a neuron of another family. All the soma are connected, so that's very complex. But here, suppose we look at only one family of neurons with one soma. But at least when there is a spike somewhere here in a membrane, then if this occurs at a point which is far from the soma, it takes some time to transmit the information to the soma. Longer time than if the spike is here. Okay? So that's this delay effect, which is taken into account here by means of...
The first model, you assume propagation occurs and prove it for modified interaction, or this is not the case?
Excuse me?
The previous model, you assume propagation occurs.
No. I just, here, I told you, assume for a while there is propagation of chaos, and assume for a while that xt, the midfield limit, has a density, then blah, 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 blow-up can occurs. And then in this slide, owing to the work by Delarue, Inglis, D.Talay, and Torre, we actually know that the system propagates chaos. At least if the initial condition, for example, is a Dirac measure, I mean, under the condition of the theory. And now what we were able to prove with James is that for this new model, the system propagates chaos to this midfield limit. So there is no surprise in the limit. Instead of having empty as in the preceding slide, we now have the integration of the kernel capital G with respect to the expectation of MS. And of course, sigma is involved in the story. The coefficient sigma is involved in the story. So I get rid of this slide. I mean, there are technical assumptions, but which are satisfied by all the models we have seen in the neuroscience literature. There is a condition on the synaptic interaction coefficients GIG in order to make a kind of a strong law of large numbers play a role, in spite of the fact that the normalizing factor is no more 1 over capital N. But anyway, we can prove again that we have the propagation of chaos in the sense that's horrible. So on the space of trajectory, you take the probability in the space trajectory, for example, the empirical measures. You take the probability distribution of the empirical measures on the space of trajectory, and these probability distributions converge weakly to the probability distribution, which is a Dirac measure, at the only probability distribution on the space of trajectory, which is the probability distribution of the unique solution to this nonlinear stochastic differential equation. Okay, so that's the story. And our condition on the synaptic coefficients is satisfied, of course, when all of them are equal to 1 over capital N, but also in these singular cases. So I prepared a lot of slides to explain the proof, but I'm finished. I was quite slow. And yes, I was really slow. Yes. So just maybe 1 minute, no more, to explain you one point. How do we prove such a kind of theorem? So following the idea of Smithman, but we have to adapt them a lot to our singular systems. This is a fixed point strategy. So you have your limit system here, depending on the expectation of a certain function of the process. So you start with any distribution. Then you compute the expectation with respect to this distribution. You plug the value into the dynamics. You look at the probability distribution of the dynamics. Then you compute again the expectation of the same functional of the process. You plug it again into the dynamics and so forth. And you iterate. And you expect that at the limit, you get a fixed point, and that the fixed point actually gives you a unique solution to the equation. So that's the story which was explained in these slides.
Point in the space of probability measures.
Yes, exactly. Equipped with the Wasserstein matrix. Okay, so just maybe just this slide to explain you, because it might be interesting for you for other purposes. Of course, the heating time distribution of the particles plays a big role in the story. And there is a nice result due to Powell's, but which can be refined a bit following an idea, a technical idea due to Marchior, which gives you a purely probabilistic interpretation formula for the density of the heating time of a given threshold by a diffusion process, one-dimensional diffusion process. So it's a complex formula, as you can see. It involves this kind of objects. But anyway, it's really only probabilistic and involves only the distribution of a Bessel, of a bridge of a three-dimensional Bessel process. So the heating time density depends only on the functionals of the bridge of a Bessel 3 process.
For which type?
And this gives, and the interesting point is that this, even if it's complex, this formula allows you to get a lot of very accurate local estimates on this density at point X close to the threshold.
At what type, for what type of thresholds is this formula?
Constant threshold.
Okay.
There are some versions of the formula for other thresholds, depending on functions, let's say, but only in particular cases. So my conclusion, open questions for models in neuroscience we would like to deal with inhomogeneous distribution of synapse with spatial temporal noises. That means not only Brownian motions but white noises, and quite open problems, or what the accuracy of numerical simulations of the nonlinear process of the particle system corresponding to these spike models. So thank you. And with a very new type of questions, the issue is not only to approximate the dynamics of the membrane potentials, but the issue is to approximate the distribution function of the heating times, which is a completely new issue in stochastic numerical analysis. So thank you very much. Sorry for
Okay, thank you very much for this nice presentation. With this difficult problem with the boundaries, it's always very difficult thing for this. It was very impressive. Okay. So, questions, please.
Let me ask for participants to go to the whiteboard to play with them. If you don't want to make a photo with Felix Berlinski, you have only one possibility to make it here.
If there is no question, maybe I ask one question. This, and
Sasha, have you a question?
You.
This last result about boundary density, when it was obtained by Powell?
Powell's.
Okay,
Powell's was a PhD student of
Williams. Rogers.
Chris Rogers. So it was published around the end of the 80s or beginning of the 90s. But its formula can be simplified a bit, as I just told you.
Could you explain the flavor of pop model? What all these functions, epsilon, k means physically? What we are talking about? What
The pop model?
Pop model. What physics you are talking about?
Very. So. No. Okay. You mean all these functions? So they are related to physical laws to be satisfied by the fluid. So these physical laws are expressed in the. They are conservation laws to be respected by the fluid. I can't tell you more than that, except that we will need some time to enter the details of the story. But they are completely satisfied by POP according to physical laws. I can give you some a short survey of the description of this function.
It doesn't have any physical names of these objects.
Oh, yeah. Yes, sir. I will tell you in a few minutes, during the break.
Stefan.
You mentioned that there was some progress for the inclusion of the Poisson equation.
Yeah.
So they obtained smoothness of the conditional propagation.
At least locally.
Okay.